Imagine Albert Einstein, late in his life, standing before a blackboard filled with elegant curling equations. He spent his final years on a singular, monumental quest. One master equation for all of nature's forces. He dreamed of a unified picture of the universe, from the fall of an apple to the twinkle of a distant star. A story both simple and beautiful. He did not complete this journey. Today, physicists carry the torch. Einstein spent 30 years searching for this, the key to reality itself. We have two spectacularly successful theories that, together, explain almost everything we observe. On one side is general relativity, Einstein's theory for the vast cosmos. It describes gravity as the curvature of space-time. Imagine a bowling ball on a trampoline. Its weight creates a dip that causes smaller objects to roll towards it. This is gravity on the grandest scales, a smooth, predictable cosmic fabric. On the other side is quantum mechanics, which governs the microscopic realm. Here, certainty dissolves into probability. The double-slit experiment shows this strange reality. Single particles act like waves, passing through two slits at once to create an interference pattern. It's a world of discrete energy packets, or quanta, ruled by chance. Herein lies the clash. The two rulebooks contradict each other. Relativity's universe is smooth and deterministic. The quantum world is jittery and probabilistic. Their languages are incompatible. When used together in extreme environments like inside a black hole, the math breaks down, spitting out infinities. This isn't just an abstract puzzle, it's a crisis at the heart of modern physics. Unlocking this mystery is key to understanding our origins. What happens at a black hole's singularity, or in the first moments of the Big Bang? To answer these questions, we need more than either theory alone. We need a unified theory of quantum gravity, a new framework bridging the gap between the very big and the very small. To resolve the conflict, physicists are exploring radical new ideas. Is space made of tiny, indivisible chunks? Are particles actually minuscule vibrating strings of energy? Could our 3D reality be a hologram projected from a distant 2D surface? These are the leading questions guiding the search for a final theory. One leading approach is loop quantum gravity. It offers a compelling alternative by focusing not on new particles, but on the very nature of space and time themselves. It takes Einstein's geometry of gravity and applies quantum principles directly. Instead of adding extra dimensions, it fundamentally reimagines the fabric of reality as a quantum object. Its radical claim, space is not infinitely divisible. At the Planck scale, space is granular. This means there are fundamental, indivisible atoms of space and moments of time. Like fabric that looks smooth from afar, but reveals interlocking threads up close. From our perspective, space-time appears continuous, but at the smallest level, it has a definite woven texture. Space-time is woven from an immense network of tiny loops. They are space. Each loop carries a quantum of area, the smallest possible surface. Where these loops intersect, they create nodes, which represent the smallest possible quanta of volume. Connected loops form spin networks that define space's geometry. These networks are a quantum blueprint for 3D space. When we add time, they evolve, creating what's called a spin foam. This picture tackles black hole singularities with the smallest volume, no infinite point. The granular structure of space provides a natural cutoff, preventing the infinite crush predicted by classical physics. Matter compresses to huge but finite density, where gravity turns repulsive. This extreme quantum pressure pushes back, preventing the singularity from ever forming. The collapse could bounce and emerge elsewhere across a quantum bridge. This quantum bounce has profound implications, suggesting our universe might have emerged from the collapse of a previous one in a big bounce. It preserves gravity as geometry but quantizes it to fit the quantum world. Challenges remain. extracting predictions and showing how smooth spacetime emerges. The theory must prove that the familiar continuous spacetime of Einstein's equations arises from this underlying quantum mesh. Like deriving water's properties from quantum rules of a single molecule. It's a monumental task, but one that promises a new vision of reality. A second, very different approach is string theory. It begins in the world of particles, not gravity. Foundational premise: the basics aren't point particles, but one-dimensional strings. These strings constantly vibrate, wiggling, oscillating. Like violin strings give notes, string vibrations give particle types. An electron is one vibrational pattern, a photon another, a quark yet another. All particles become notes of a single underlying entity, the string. A third, mind-bending idea is the holographic principle, which suggests our three-dimensional reality is a projection. It proposes that everything we experience is fundamentally encoded on a distant, lower-dimensional surface, much like a hologram projects a 3D image from a 2D film. Imagine a vast cosmic volume. The principle states that all the information contained within that space, every particle, every field, every interaction, can be fully described by a physical theory living only on its boundary. The rich 3D world inside is simply a representation of data stored on that surface. This radical concept grew from a puzzle surrounding black holes. Quantum mechanics says information can't be destroyed, so what happens to it when an object falls in? Jacob Bekenstein and Stephen Hawking made a startling discovery. They found a black hole's information content is proportional to the two-dimensional area of its event horizon, not its three-dimensional volume. This was a profound clue that information for a volume of space might actually live on its boundary. This idea found its most precise form in the ADS-CFT correspondence. This powerful conjecture provides a mathematical dictionary, linking a theory of gravity in a higher dimensional bulk with a quantum field theory on its lower dimensional boundary. The two descriptions are entirely equivalent, like two languages describing the same reality. This duality is a powerful computational tool. It allows physicists to map difficult gravity problems onto more manageable quantum problems. For instance, the chaotic behavior of quark-gluon plasma in particle colliders can be studied by modeling a simple black hole in the corresponding higher dimensional space. The principle also offers surprising insights into condensed matter physics. Ultimately, the holographic principle suggests that space-time itself might not be fundamental. Instead, space and gravity could be emergent phenomena arising from quantum interactions on a distant boundary. This doesn't mean our world is an illusion. The hologram is perfectly real to us. It simply means the fundamental description of reality may be flatter and stranger than we ever imagined. We stand at a fascinating moment in the history of science. Three compelling, incomplete paths: loop quantum gravity, string theory, and the holographic principle. Granular spacetime, higher dimensional strings, a projected universe. Experiments push forward, smashing particles, mapping the infant cosmos, and listening to spacetime itself. Einstein lit the path, and a new generation walks it with mathematics, supercomputers, and extraordinary tools. The clash is not failure, it is a signpost toward deeper truth. The dream of a final theory is alive. Comment gravity after 60+ seconds for your free quantum guide. Subscribe for next week's physics mystery.